this is Rohit Verma, and welcome back to the Backbenchers Academy by Rohit Verma. And today we are here to study these two topics, critical angle and TIR, which is total internal reflection. So I'm going to tell you what exactly critical angle and total internal reflection are, and what exactly are the practical applications. So without any delay, let's get it started with our very first topic being critical angles. Alright, so our first topic, that is critical angle. Let's understand what exactly a critical angle is and how it actually comes up to implementation. So see, generally what happens, if suppose we have over here glass and air, and we've got a ray of light which passes from glass to air obliquely or slantly. So this is called the incident ray. Incident ray. At this point of intersection or the point of incidence, we draw a normal, being this is our angle of incidence. At this angle of incidence, we are passing the ray from glass to air, which is denser to rarer medium. So it's something like a car going from glass, meaning denser medium, which means like a car is going from a narrow street to a highway, because here air, the intermolecular spaces are lots. There's like a lot of space over here. Here the space is less, which means that the ray will get ample of space to bend off, which means ideally the ray should have gone this way. If there was no deviation, if there was no particular bending, that means no refraction would have taken place, the ray would have gone like this. But here we're changing medium and this angle of incidence is not zero, so it will bend. It will bend away from the normal this way. And this particular angle over here, this angle is the angle of refraction R. Refraction. That's the angle of refraction to us. This is what normally happens. But what if this angle of incidence becomes a critical angle? Because critical angle is a special angle of incidence in a denser medium when a ray of light is passing, under which the angle of refraction becomes 90. So that's how we define it. When you define critical angle, you can say that critical angle is defined as the special angle of incidence of a denser medium when a ray of light passes from denser medium to a rarer medium, under which the angle of refraction becomes 90 degree. That's how we define the critical angle. It's a special case of angle of incidence. So let's hear it. See, if this is again glass and air, and another ray passes, which is the incident ray. This is our normal, let's suppose N1, N2. I can name it here as well as N1, N2. And this angle, which is angle of incidence here. Now if this angle of incidence becomes equal to angle of this critical angle, which is I equals C, if this happens, this angle R turns to be 90, so the ray bends by 90 degree. That's going to be R equals 90 degree. The ray bends like this. So critical angle is the special angle of incidence in a denser medium when a ray passes such that the angle of refraction becomes equals to 90. As simple as that. Alright, now let's understand, is it always necessary that angle of incidence in the denser medium will be equal to critical angle? I think no. Of course, it can be less or equal or greater than the critical angle, because critical angle is a special angle of incidence as we just discussed, and that depends on the medium. For example, for glass, let's say, the ideal critical angle value is 42 degrees, and the same value is different for different mediums. So let's understand what happens if the angle of incidence is different with respect to critical angle. If it's less, what will happen in that case? If angle of incidence is greater than critical angle, what happens in that case, like we just discussed? And if it's greater than critical angle, then what happens in that case? So let's hear it for the first case over here. If the incident ray is coming where angle of incidence is less than critical angle and the ray is passing from denser to rarer medium, let's say like glass to air, in this condition what exactly happens is something like what happens when we stand in front of a normal glass, a transparent glass. You can see things on the other side, but if you see carefully and you observe, you can also see a blur reflection of your own, which means both things happens, reflection as well as refraction. Both the things are happening. So the same thing happens here, which is a normal case. So what will happen over here is that the ray will bend away from the normal, of course. Ideally it should have gone straight. It is going away from the normal. This is angle of refraction. Refraction. Fine. This thing is happening in a proportion of almost 90% of the light is refracting, but there's a minor particular value of almost 10%, can be less or more depending on the type of glass, which will reflect as well. This will bounce back. This is angle R, which is the angle, I'm defining it as angle of reflection. So herein the light reflects, it comes back. So if you stand in front of a glass, transparent glass, and if you observe, you can see things on the other side of the glass, and as well as you can also carefully observe a blur reflection of yours. This is what happens in case 1, exactly the same. This is a normal case. This is a slightly unique case where angle of incidence becomes equals to the critical angle, and as we discussed, now the angle of refraction of light will become 90. So the ray will pass like this, just as we discussed. Right. This was case 1, that's case 2. Talking about case 3, what happens if the angle of incidence in the denser medium is greater than the critical angle? In this concern, what will happen is a 100% reflection, which means that the 100% light energy which is coming from here will be reflected as it is. This becomes angle of reflection. And this case 3 is also termed as the condition of TIR. This case 3 has a special name given to it, which is TIR. That means total internal reflection. As the name says, TIR. Total means 100%, because here also the light is coming as 100%. Internal, because it's inside the denser medium. Reflection, since it's completely reflecting. So total internal reflection. These are the 3 cases which we must know, and we can apply the appropriate condition according to the given value of incidence, whether it is less than critical angle, equal to critical angle, or greater than critical angle. Now let's continue further to our next topic, which is total internal reflection and its applications. Let's understand first the term total. Complete. Total means complete. Internal within the denser medium. Reflection, bouncing back of light in the same medium. This is the phenomena in which a ray of light which is incident in a denser medium at an angle of incidence greater than the critical angle will bounce back completely with a 0% energy loss. Means 100% light energy coming will bounce off 100%. No refraction will happen, only reflection will happen. And this has 2 major applications in real world. One is in diamonds, second is in optical fiber. Let's first understand one by one the applications. Diamonds, if you talk about, are very lustrous, they shine a lot. Why? Because of total internal reflection. Let's understand really how. When you talk about diamonds, diamonds actually are pretty expensive, as we all know. But the amount of the worth of a diamond depends also on how are they cut, the angle that they're cut at. So if a diamond has a very unique cut or a very special sort of a cut, the angle at which they've been cut off, then it will be worth more than the usual diamonds, because of the fact that that cut actually creates the impact of the total internal reflection. Since in a diamond, when a ray of light is incident, even a minor ray of light is incident, it comes inside just like this. This is a diamond. Generally the shape of a diamond is like this. So a ray of light, this is the incident ray. It comes in, the source can be anything. The source can be sun, the source can be a bulb, can be a tube, can be a CFL, whatever. So when this comes inside, the angle of incidence which is created is always greater than its critical angle, because the critical angle value of a diamond will be small. So it will always be greater, due to which it keeps reflecting back and forth until it reaches to a certain angle where it can actually escape out. Let's say it escaped. So when it will be seen, let's say from here, if somebody is observing this way, the person will be able to see the diamond shining from multiple sides, because the light has been reflected so many times that it creates an impact of multiple luster, or you can say luster or shine from multiple angles. This is exactly what happens in case of diamonds. So TIR is implemented in diamonds, number 1. Second, optical fibers. Let's understand. The word optical says something relevant with light, right? Fiber is a type of material which is quite similar to plastic. Just like in cell phones, we have these tempered glasses, which is nothing but glass, because when you crack it off or you take it out and you bend it, it will break like a glass and keep breaking off. But in case of a fiber, there are even fibers which have replaced these tempered glasses now. But in case of fiber, when you bend it, what will happen is it won't really break. It will create a line over there, and that line will have a bend of that surface. It will bend. It won't really break. It will just create a line because it's not really breakable as it's not as easily breakable as glass. So fiber is another such material associated like plastic, just like PVC is one similar kind of a material which is used for bend, those curves made around the wires so as to protect them as an insulator. So in optical fibers which are used in telecommunication, like we have at times some network connections with the speed of broadband speeds of 100 Mbps or even beyond. For them we use optical fibers. Let's assume you have an internet connection of any company, let's say X. That X company will have an office established with its telecommunication towers spread all around this area wherever it is actually providing its services. Those towers will have some wires which will be, you can say, transported to these civilian areas. Like near your house, you will have a certain electric pole with a particular box which resembles something like this this sort of a box with wires connected through it, and those wires will be reaching to your house. And if you have an optical fiber connection, I'm pretty sure your speed will be really good. Wherein, why exactly we have 100 Mbps or a better speed in optical fibers? Because when signals are transmitted in optical fibers, these optical fibers are designed such that the same thing happens. Angle of incidence turns out to be always greater than the critical angle, since their critical angle will also be less. So the signal travels again and again, getting reflected back and forth this way up. So the signal is internally reflecting within the optical fiber, and in total internal reflection, as we know that 100% light energy is reflected, it means that in terms of optical fibers, we'll have a 0% losses. So automatically the system becomes more and more efficient, due to which we will have a greater speed, because this sending and receiving of signals is happening very smoothly with a negligible, next to nothing or next to a 0% of losses. That is the reason why optical fibers are actually used for a better telecommunication services and better internet services, wherein the phenomena actually involved here is total internal reflection. Alright, so everyone, let's understand what is the relationship between mu and c, where mu means the refractive index of a medium and c means the critical angle of the medium. So this is the major relation, which is the formula as well. That is mu equals 1 upon sine c. This side is the trigonometric ratio, and mu equals 1 upon sine c is the major formula. Where mu is the refractive index, as we can see, of the particular medium, and c is the critical angle of the medium. So if we actually simplify this particular relation, we can say in simple terms or simplified terms, mu is inversely proportional to c. Mu equals 1 upon c. That means that if we increase the refractive index of the medium, the critical angle will reduce. So mediums that are denser, like if you compare with water, diamond is denser, glass is denser, they will have less value of the critical angle. It means, now what does that mean if the medium has a less critical angle? It means that if a medium has a less value of critical angle, there are more chances, or there are easy chances or probabilities of total internal reflection happening, because lesser is the critical angle, easier the TIR can happen. So if you see here, water, in which mu is less because it is less dense. Diamond, mu is more because it is more dense. Critical angle of water is approximately 49 degrees, and for diamond, critical angle is approximately 25 degrees. So if you can see the difference, the one which is more dense has a lesser value of critical angle, and the one which is less dense has a greater value of critical angle. So I hope you understood that they're inversely proportional. Similarly, critical angle also depends on two more factors. One is color or wavelength of light, wherein dp means directly proportional, means higher will be the wavelength, more will be the value of the critical angle. So red color has the highest wavelength, that is why it's used in the danger signals. So that doesn't deviate and it's easy to be visible. Red color, being having the maximum value of wavelength, will have a greater value of critical angle, or the greatest value of critical angle out of all the 7 colors of the white light. Similarly, temperature, it is directly proportional to temperature as well. dp means directly proportional here as well. Means at a greater temperature, the critical angle will be higher, whereas for a lesser temperature, the critical angle will be less. Now, let's talk about some questions which are associated with the ICSE board examinations, or even CBSE also can ask the same. Uh, these questions are based on three prior conditions that we've studied regarding the critical angle, case 1, 2, 3, their implementation or uses. Wherein, let's talk about these questions, what do they ask, and how will the question be generally given. These questions generally are based on either prisms or either rectangular glass slabs, wherein you will be given a prism. It's like we have two questions here. We'll go one by one. They're very, very important over here. By the way, I've mentioned here is very important. We'll go question by question. The first question says we have a triangular cross section of a prism which is ABC, which is an isosceles right angled prism. One angle is 90, two are 45 each, and an incident ray PQ is coming over it. The question will demand you to actually complete this entire diagram with, they've shown you how is the ray entering, how will it exit, or how will it come out, emerge out of this prism, that you will have to tell. Wherein it's very, very important to label everywhere that exactly what angles are being involved. So this is coming perpendicular, this will be told to you. In most of the cases, 90% of the cases, or 99% of the cases rather, I can say. So here, first of all, we see this is coming perpendicular, which means angle of incidence is 0. Many students do a mistake here. If it's coming perpendicular, they write angle of incidence equals 90 degree. That's wrong. And I would appreciate if we can please write this as I1. That is our first angle of incidence. There will be more afterwards. So since angle of incidence 1 is 0 over here on the surface AB, so it comes inside straight away, no bending. So this angle being 90, this is 90 as well, 90, 45. Now we are applying the angle sum property of the triangle, which says that all the angles must add up. The three angles must add up to 180 degrees. So this is a triangle formed here. Let's say this, we name this as PQR being the other point. At point R, this is for 90, 45. This also becomes 45. Now whenever a ray touches another surface of this prism, we have to draw a normal. So first of all, let's replace this R over here and let's draw a normal over here. Let's say this. Being the fact that a normal is always perpendicular to the surface, so this angle is 90, out of which 45 is this one. So remaining also is 45. Now one thing to note, everyone, all the students, please note this, that the value of C or critical angle for glass is always taken as 42 degree until and unless the question has given another value. If the question says that the given particular prism has a critical angle value as 60 degrees, that's a different thing. Then you will take only 60, not 42. But if it is not given, it is short to be taken as 42 degrees. And now, if it is 42 and we compare angle of incidence, this was, by the way, our second angle of incidence, I2, which is equal to 45 degrees here. 42, 45 and 42. Angle of incidence is more than the critical angle. That's the condition number 3, case 3. So here TIR happens. TIR says that now the reflection will happen. If it is incidence angle is 45 according to the law of reflection of light, incidence angle will be same as reflection angle. So this also is 45. And the other remaining angle also is 45. Due to which, if you see another, so P, Q, R, let's say this is S. At this point S, now we have framed another triangle in which these two are 45. This one becomes automatically 90. Wherein here, since the ray is coming perpendicular, it means that now we have again another third angle of incidence being 0, not 90, 0, it's 0. So it goes out straight away, and this is how we've completed the path of this ray. It means that the question will tell you only how the ray is entering, how it will exit or escape out, that we'll have to figure out. And there are two rules we are following over here. It's very simple. One, angle sum property, whenever we have a triangle being formed with two angles given and one angle missing. Second thing are the three conditions of the critical angle. We have to compare which condition are we implementing. Now this was our first question. I hope you all must have understood. Rest you can rewind and see this video in case if you didn't understand. And secondly, let's talk about now another question which says we have another surface, triangular surface area, cross section area of a prism XYZ, which is, this is 90 degrees, this is 30 and 60. This is not an isosceles right angle prism. It's a separate prism with two angles different, that is 30 and 60 respectively, and one being 90. So this is ray, let's suppose this is PQ again, which is perpendicular to the prism. So since being perpendicular, it was obvious that I1 is 0 degrees and it passes straight away, no bending. This is 90 as well. 90, 30, this becomes 60. Now this is point P, Q, R, let's say R. at this point R, now we need a normal. Every time the particular ray hits or strikes to a surface, we need the normal. Because without the normal, we can't tell what is the angle of incidence. So here we have this 60 degree. So this remaining angle becomes obviously 30. Because perpendicular, this normal means perpendicular to the surface like this. So if one portion, this whole angle is 90, one portion is 60, other is 30. 30. And this is 42, critical angle. It's less. Case 1 class. Case 1 says, whenever angle of incidence is less than the critical angle, the ray will show reflection as well as refraction of light, what happened earlier. But majority cases, or rather 90% of the case was refraction, so we'll do refraction here. We will let the ray pass out of the prism, wherein, if we see, ideally the ray could have gone straight. This is the normal, but we are going from glass to air. We'll go away from the normal. We have more space now. So we'll move on like this. We'll move out like this, with this being our angle E. What is angle E now? Angle E is the angle of emergence. What is the value of this angle of emergence? We don't really know. We can't really calculate first of all over here without actually performing this practically. We'll have to perform an experiment. So what really you're supposed to do is just simply mention E being angle of emergence and no need to mention any values. I hope this was understood, and we've already taken this ray out of the prism, so we've shown the path of this prism. We wanted two angle of incidences, we just have to label this I2 in 30 degree. And such questions do come in majority cases in the ICSE examinations. They've been a part of the examinations question papers from past few years, and I'm sure, there are major cases or chances that this will be, a part of the further question papers as well. So you must take care, this is very, very important. So that's it, it's easy.